taking a look at worksheet number 7, question number 3, which was one of the 2 questions that was for homework last night. Number 3 says, repeat question 1B above, but with a third charge below the second charge. I'll draw the picture here so we don't have to go back to question 1B. We've got charge 1 right here, which has a charge of positive 5.00 times 10 to the negative 5 coulombs. Got another one right here that we're going to call charge 2. It's also 5.00 times 10 to the negative 5 coulombs. And then we've got charge 3, which is down here. It has a value of negative 2.50 times 10 to the negative 5 coulombs. We have the distances. They're given to me in the question in centimeters, but I'm going to convert them right away to meters because we know we're going to use meters here. 2.5 centimeters is 0.025 meters. And 2 centimeters is 0.020 meters. Now we want to find the net force on object number 2, charge 2 here. When we do this, we pretend that we only have 2 charges at a time. So I want to find the force between 1 and 2. Pretend 3 doesn't exist, okay? Just ignore it. Cover it up. 3's not there. Look, it's gone. Now, let's look at 1 and 2. Okay, I think what most people struggle with on these questions is not so much the mathematical analysis, but rather the free body diagram. Let's look at 1 and 2. 1 and 2 are both positive charges. As a result of both being positive charges, what's going to happen to them? Are they going to attract or repel, Natalie? They're going to repel. So if they repel, which way is 2 going to be repelled? To the right, away from number 1. It's pushed away from number 1. Now I'm going to call that F12. You can call it whatever you want. Okay, I call it F12 because the notation helps me to distinguish between the forces, right? F12 is the force of 1 on 2. You want to call it force K. I don't care, okay, as long as you understand what it represents. All right, now we're going to look at the force of 3 on 2. So we're pretending number 1 doesn't exist now. 3 and 2 are opposite charges. One's positive, one's negative. So what are they going to do? Are they going to attract or repel each other, Jessica? Yeah, they're going to attract each other. And if they attract each other, number 2 is going to go which way as a result of that attraction? Down towards number 3. Now, some of you look at this and say, well, like, oh, I thought I had to draw number 3 going up. Well, no, what are we trying to find the force on? 2. If we were trying to find the force on 3, then that would have been the one to draw. But if we're finding the force on 2, just draw what happens to 2 as a result of the force. All right, there's my 2 forces. I can calculate those 2 forces. In fact, in question 1B, I already did calculate those 2 forces. F12 was KQ1 Q2 over R squared. And the value of that worked out to be 3.596 times 10 to the 4. Now, the value of F32, we already calculated as well earlier on. It's KQ3Q2 over R squared. And the value of that works out to be 2.8094 times 10 to the 4 newtons. Now, how do we combine these? If this is question 1B, all we do is add these together, right? 3.5 plus 2.8 gives me whatever. I have to pay attention to negatives. Well, what do I got to pay attention to here? It's not so much the negatives, kind of. Yeah, like we got to create something with a funny angle, right? We got to create a new triangle, and we have to add them up vectorially using the Pythagorean theorem. So I'm going to say F12, which has a value of 3.596 times 10 to the 4, gets combined with F32, which is 2.80942 or 94 times 10 to the 4, and then we combine them. We solve for the value of F, and we solve for the value of theta there. F gets solved by the Pythagorean theorem. Its value works out to be 4.56 times 10 to the 4. And theta gets found by the inverse tan of opposite over adjacent, and that works out to be 38.0 degrees. Now, we are not going to express this 38 degrees south of east because we're not given the north, south, east, west frame of reference here. Okay, we're not told that it's north and south. Okay, we just know that it's to the right and whatever. We could say that this is 38 degrees down from right, or quite honestly, the easiest thing to do is just to say, look, we have our angle labeled on the diagram. Okay, if we label it in the proper spot and we calculate the right number, then that's good enough for this question. We can't really do a north, south, east, west thing. All right. So 38 degrees is a good enough answer as long as you have theta labeled on a picture. If you just wrote 38 degrees and didn't have a picture labeled, then that wouldn't be quite enough. Let's take a look at a couple examples from Concept 20. These special, wow, these are hard examples that you should not lose. Bonus questions. As it turns out, actually, there's only one that's really hard. There's another one that's kind of hard. The other two are not too bad. The one that's squared off, that's question number 2 at the bottom of the first page. That's really, really hard. Okay, and I would suspect that if I gave that to you right now, most of you would probably not get that question. That's why we're going to go through these 4 questions together. I'm not setting you free to work on them and struggle. We're going to work on them together. And then if you happen to ever see something like that again, well, then you'll have to do it yourself the second time around. Okay, so what do we got going on here? We've got this these 2 strings, actually, 2 strings attached to a ceiling or the top of a box or something, and 2 identical conducting balls, 1 and 2, on the ends of the string. Each ball has a mass of 25 grams. It's hanging. They become equally charged. So one's +5, the other's +5. One's -3, the other's -3. They're equally charged, and they come to rest. What does that tell us? They come to rest. They're stopped. They're not moving. What's a word that could describe that? An E word that could describe that. Equilibrium. Yeah, that's a word that you use in physics and chemistry and biology. And it always means, in any context, it means balance, right? We've reached a point of balance. In physics, equilibrium means specifically forces are balanced. So here we've got balanced forces. In other words, the net force has to be 0. If something's at rest, the net force is 0. All right, let's look at the question here. It says, the electrostatic force between the charged balls can be best described as what? Well, if these things are not straight down, they must be being pushed away, right? So that's got to be a repulsive force. And if it's a repulsive force, it's got to be due to them both having the same type of charge. So we're going to say it's repulsion due to similar charges, like charges. Now here's the tough one. This is the reason I squared it off so you could draw attention to this one. What's the tension in the thread that's supporting one of them? Any ideas here? Like, I'm not asking you, can you solve this question right now? I'm just asking if you have an idea. If there's something in this question that you see that you can do, even if you don't know if it's going to lead to anything or not. Philip? Okay. We know that each of these identical conducting balls are 25 grams and they both experience the force of gravity. Let's pick one, right? We want to find the tension supporting in the thread supporting one of them. Let's pick one. Okay, let's pick ball number 2. And Philip said we can find the force of gravity. It's equal to 0.025 times 9.81, which I think gives me 0.24525 newtons. Okay, there we go. Is that going to lead me to an answer to this question? Well, as it turns out, it is. But if I was looking at this for the first time, I may not know that. That's okay. I've done something that's correct. Whether it leads me to an answer or not, whatever. You don't know what to do something. Phil just did something. Okay. Anything else? Anything else that anybody sees here? Yeah. What kind of force is that between the two balls? Okay. And the electric force on the second ball, if we're drawing the force of gravity on the second one, then we better stick with the second one, right? The electric force would be this way. How am I going to find that? KQ1, Q2 over R squared? What's R? What's Q1? What's Q2? Well, we have K, but you know what? Hey, so we weren't able to find FE, but you still told me something correct. There's an electric force between them and it's acting to the right. So I'm further ahead than I was before. Just got to get a little bit further ahead now. Oh, yeah, you could actually. You could find that distance. Yeah. Still don't know what the charges are though, so we're getting there. Yeah. 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 Well, there might be a way to turn that around actually. Yeah. You'd have to include, yeah, what would the force be though? See, if you know the charges are identical, if you know what the force is, you can find the charge, right? But if you don't know what the force is, then you can't find the charge, right? So it's kind of a circular thing, right? Josh? Oh, okay. Okay. So are you saying this, like this angle right here? Okay, you're getting there. You're definitely getting there, but you're skipping a step in there, and you might be thinking in your head, or I'm not sure. I just want to go through it with everybody just in case here. We're going to call this Ft, the force of tension in the string. What did we say a minute ago? This is in, what's the E word? Equilibrium. It's in equilibrium. The forces are balanced. That means that if there's a downward gravitational force that's equal to 0.24525, then there has to be an upward force that balances that, right? There's only one upward force here, and it's the y component of Ft. Ryan's nodding his head like, "Oh, I knew what to do with this question." Ryan, what's the value of the y component of Ft? Oh, even easier. Even easier. What's the value of the y component there? 2.24525. Look, if there's a downward force of 0.24 newtons, then there has to be an upward force of 0.24 newtons. Otherwise, it wouldn't be in equilibrium, right? Now, there's a force to the right, the electric force. Well, there's a force to the left here. I'm going to call it Fx, the x component of the tension. I don't know what that is, but I do know that it's equal to the electric force, whatever that is, right? Okay, now I think we're there now. We know what this angle is right here. We know what the adjacent side of this triangle is. We want to find the hypotenuse. Why don't we just say cosine 45 degrees is equal to adjacent 0.24525 divided by hypotenuse, the tension. And the tension ends up being, I think it works out to be 0.347 when I do the math there. Does that make sense to you guys? Like this green force down is balanced with this blue force up. And this green force to the right is balanced with this blue force to the left. They have to be equal because otherwise it won't be in equilibrium. We're not saying that now there's three forces acting up now. There's one, but the x component of it and the y component of it are what balance the electric force and the gravitational force. Now, what if I asked you one more thing in this? What if I asked you, what's the value of the electric force? What's the value of the electric force? It's not what we're asked, but you can imagine in this unit of electricity, that's something that they could very easily ask another time. Philip, what would you do then? Yeah, it does actually. Let's assume for a second the angle wasn't 45. Let's say it was 42. If it's 45, we know it's going to be the same value as this, right? Yeah, probably using sine, right? Sine 45 degrees or 42, whatever, equals fx over, actually, you know what? I don't think I want to do that. I got the hypotenuse, 0.347, but if I had been asked for just the electric force, I wouldn't have the hypotenuse, right? Probably tan, yeah. Tan 45 degrees is equal to fx over 0.24525. And lightning fast calculations here. Watch how impressive this is. Fx equals 0.24525 newtons. Okay. How was I able to do that one so quickly in my head? Holy cow. Yeah. It has to be the same because the angle's 45, right? Is that okay? We're asked for one thing there. We could have been asked for the second thing easily, but we could have, if we can get the first one, we can get the second one, I think. Yep. Well, that's the x component of the tension. Yeah, but remember that we've just found the x component of the force on one of these conducting objects. Now, that is the same as the electric force. Now, Philip is saying there's two conducting objects because, of course, you can clearly see that there's two conducting objects here. And they're repelling each other. So when we need to double it or something, the answer is no. If the force, the electric force on this conducting object is equal to the x component of the tension force on this conducting object, then if I had done the analysis with this one, I would have got the exact same force. Now, if I was to give you a question like this, say, find the force between object A1 and object 2, you would have calculated it to be, let's say, 10 newtons. You wouldn't automatically say now, oh, well, that's a 20 Newton force, right? It's 10 newtons acting on this guy. It's 10 newtons acting on this guy. In this question, it's 0.245 acting on this guy, and it's 0.245 acting on the other one as well. Okay, the x component of the tension that's holding that one conducting object in place has to be the same as the electric force on that one conducting object, right? Make sense? All right. Let's move on to question 3, which is a little bit tricky actually too, but not quite as bad as question number 2. If the charge on B1 is tripled and the charge on B2 is reduced to 1/3 of its original amount, what would happen to the angle between the two? Well, let's find the force. The original force is KQ1 Q2 over R squared. The new force is what, K times 3Q1 times Q2. No, sorry, times a third Q2. Because one of them is tripled, one of them is cut by a factor of 3. Which gives me what? 3 over 3 is 1. So my new force is the same as my original force. Hey, if the force is the same, what's going to happen to the angle of deviation? It's going to stay the same for both of them. Now, some people are going to look at this and say, yeah, but charge 1 is like 9 times the other one, right? Charge 1 became 3, and charge 2 became 1/3. Okay, how can it be the same angle of deviation when it's different charges? What's important here is that the force still ends up being the same. And if the force is the same, it's the same on object 1 as it is on object 2. So they're both going to still deviate the same amount. Now, if I made this 6, instead of 1/3, the force would be bigger now, wouldn't it? But the force would be bigger on both of them. So here, let's keep that 3. Let's say I changed it to 6. Well, now they would both move a little bit further out. They would still have the same angle of deviation because the force on one is the same as the force on two. Just now that both forces are a little bit bigger than they were before because the charge is bigger. That make sense? How could I change this? How could I change this to make this one not be spread apart the same amount? How could I change it so that that one gets further up? Yes. If this one has a bigger mass, the same force will have more of an effect on the smaller mass. It would still be the same force, equal and opposite forces, but because they're different masses, they deflect different amounts. Go back to the question though. In this question, it said they were identical. And if they're identical, then they have equal masses. So regardless of what the forces, they're going to be the same angle. Okay, last question. The electric force between the particles is F newtons when they're 9 centimeters apart. They're moved toward each other until they're 6 centimeters apart. What's the force between them become? Well, there's possibly more than one way to solve this. The way that I did it was a variable value changing thing. I said my original force is KQ1 Q2 over R squared. And I said my new force is K times Q1 Q2 over, what do you think I'm going to make R now? Yep, 2/3 R, right? It was 9, now it's 6. I don't care about the 9 and the 6. Hey, maybe it's 9 and 6, maybe it's 15 and 10, maybe it's 30 and 20, I don't care. My new distance is 2/3 of what my old distance was. So it becomes KQ1 Q2 over 4/9 R squared, which becomes 9 over 4 times KQ1 Q2 over R squared, which is 9 over 4 times the original force, D. Your homework for tonight, page 538, numbers 4 to 10. In addition to that, we've got practice question set number 10.